All right,
And it's my
then.
pleasure to introduce Yusu Wang from The Ohio State University, who will be speaking today on graph reconstruction via discrete Morse theory. Thanks, Yusu.
Thank you, Henry, for organizing this. And I thank whoever is watching now or either now or later. So as Henry said, I want to tell you a bit about some of our recent work on applying as well as providing theoretical understanding of discrete Morse theory-based graph reconstruction framework. So this is a combination of several pieces of work, and I'm going to mention my collaborator through the talk. Okay, so I guess I don't have to say much to motivate the study of graphs. I mean, graphs, this object occurs rather naturally in many applications. So, for example, in many cases, like the road network reconstruction we're going to mention later, the hidden space where your data sample from can be graph-like, like the road network behind a bunch of sampled trajectories. Or here, this is the simulation of dark matter in the universe, and the underlying there's this filament structure, which is also graph-like. Okay. Or in many other cases, we can also argue that it doesn't have to be geometric graph. An abstract graph can also is a one very simple yet a natural way to model nonlinear structure behind data. Okay, so you could have, say, Twitter data, and by extracting the one-dimensional skeleton behind it, you may be able to discover how the topics evolve, how they then merge, and then how topics then split into different subtopics and so on. Okay. So in the past few years, I have been very interested in using geometric and topological ideas to develop different kind of graph analysis algorithms under different settings. Typically, we focus on providing both theoretical understanding and guarantees. So what I want to talk about today is on graph reconstruction. Okay, now to have an effective algorithm to reconstruct a hidden graph from input data, really the strategy should depend on what setting you are in, what type of input data you are given. Okay, so for example, in the literature, one of the setup is as follows. It could have a set of points sampled from a hidden geometric graph, okay, in some ambient space. And these points are sampled within bounded Hausdorff error, or it could be in the metric setting where the points are sampled with bounded Gromov-Hausdorff error. Okay, so basically all these points are close to hidden geometric graph, and you want to reconstruct this hidden graph. Okay, so for this setup, one of the approach by Yanjie is they basically use local homology, look at the local neighborhood of every point, and then classify which point could be the junction nodes, which is not, and then further connect those junction nodes. Okay, so this is one type of approach. Another type of approach for this setup is that they use the topological concept of reef graph. They first construct some sort of a complex, say the RIPS complex from this point samples, and then use the reef graph of certain specially chosen descriptive function to help you to reconstruct the hidden graph. Okay. Now, I listed these two approaches because both of them, this type of approaches, actually, some theoretical guarantee can be obtained. Okay, so in the reef graph setting, the theoretical guarantee of how good you can reconstruct the graph are given in the paper by Chazelle et al. Okay, but this kind of setup is not very robust when your input points has some kind of ambient outlier type of noise, okay? And this is a setup actually we are interested in. I'm interested in today's talk where I would like to have an effective graph reconstruction algorithm which can also handle this kind of ambient noise, okay? In particular, I'm going to describe this framework, which is what I would call it persistent guided discrete Morse based graph reconstruction framework. Okay? I'm going to start by giving a motivating application from the road network reconstruction. Okay? Then I'm going to talk about how we further provide theoretical understanding, including some guarantees on the reconstruction of the graph. As I said, this is this is a combination of several pieces of work, and my collaborators here includes my former students Suyi Wang, Yanjie Li, my colleague Tamal K, and our joint students Jiayuan Wang. Okay, so let's first look at the following very natural application. where we're given a whole bunch of GPS trajectories. The user use their mobile phones, track where they're going, and then they supply this to some common public available database. Okay, so we have a large collection of GPS trajectories, and the goal is that from this trajectories, we want to reconstruct the hidden road network automatically. Okay, now the problem clearly is important, especially given that with the rapid increasing amount of user-produced GPS trajectories by their mobile phone or other GPS-enabled devices. Okay, so we want to be able to automatically either reconstruct the road network or update the road network. Okay, because of its importance, a lot of approaches has been proposed and developed in the GIS community. There are two major challenges. One is that the trajectories can be very noisy, especially say in the downtown area when the GPS signal gets bounced back and off. So here, what I'm showing here is actually the GPS traces collected by taxi drivers from Beijing. As you can see, especially, hope you can see my mouse cursor, especially in the downtown area, the trajectory can be really noisy. Okay, that's number one. The second challenge is that the signal can also be rather non-uniformly distributed, by which I mean that, for example, in downtown area, there will be more people passing around, so there will be more sampled trajectories, while in places, say a little bit residential area or more rural area, the road will be less sampled, okay? So there's a non-uniform distribution of the signal span. Here I'm showing a picture here. Here actually, as you can see, around the major road or the small roads around it, the sampling density can be very different, okay? So both of these cause challenges in the reconstruction of the road network, okay? Because of the noise, very often, many of the previous methods, they use local information to help them to decide whether you're at the junction nodes or you're on the road or off the road, okay? And this local information is rather sensitive to noise, okay? And also, in most of the previous methods, some sort of thresholding is involved to remove noise. And this, because the input signal can be non-uniform, this makes the thresholding, finding a universal threshold very challenging, okay? So in general, the identify the junction nodes reliably and also connecting them in the most feasible manner is not a trivial question. Okay. So what we're going to do, what I'm going to describe now, actually. So what we're going to do is the following. From the input trajectory data, we're going to first convert this into some sort of density field indicating where we sampled in the planar domain, okay? And then I'm going to use a persistent guided discrete Morse-based reconstruction framework to recover this hidden road network, okay? So because we're using the global topological structure of this density map, okay? This makes the method more robust against the noise and the small gaps, okay? It can also identify junction nodes very reliably, but also robust against the non-uniform, because we're not going to use any global threshold. It's also robust against the non-uniform sampling in the input data, okay? And as you'll see later, also the approach conceptually is very clean and implementation is also very simple. Okay? You can also extend this framework to other applications like a map integration, I'll mention later, map integration and augmentation, okay? So the results actually from this very simple framework actually beats the previous state of the art results. Okay, I want to remark that so this using persistence in combination with the discrete Morse theory to recover certain either 1D or 2D other skeleton type of structure, this idea is not new. Okay, it has been studied in Guiula's PhD thesis, in Vanessa Robbins and her collaborators' work, and include also in recently in Soulsby's work, where he used this approach to study the filament structure in dark matter density field. Okay, so what I'm going to present here, number one, we're going to show how this is adapted to the road network reconstruction application, including extended to map integration and augmentation. More importantly, later I'm going to show that. So I'm going to focus on the power of this framework on graph reconstruction. Later, we're going to provide further theoretical understanding, which make this algorithm even simpler, and also show that under certain noise model, we can provide theoretical guarantee of the reconstruction output. Okay. Okay. So the main idea is very simple. It's quite natural. Now, our input is a bunch of GPS traces. These are the curves in this picture. Okay. Number one, first step, I said that we convert this into some sort of density field, which indicate how densely the GPS traces is sampling around this. Okay, so here we just did some simple KDE density estimating. Okay, so now we assume that our input now is actually a scalar field F, defined in this case by now. I'm drawing the picture using the planar domain I. Okay, this is the planar region. But the approach works for a region I in any Euclidean space RD. Okay, so we have this. Assume now our input is the scalar field defined on the domain I, where the high value of this scalar field indicate a high signal value. Okay. Now we can view the graph of this function as a terrain. Again, in the 2D case, it's rather intuitive. We have this terrain as shown on the right. Okay. And now we want to recover the roads underlying this terrain. Okay. Even though that the input GPS trajectories can be noisy, can sample also places off the road, but still we imagine that for points on the real road underlying this terrain on the real road network, the density locally should be higher if you going across the road, off the road, basically. Okay, so this suggests that maybe the right way to capture the road is capturing the mountain ridges of this terrain, because those are the places that if you go off the mountain ridges, you basically descend to some valley next to you. Okay, your density would then decrease. Okay, so basically we want to use the mountain ridges of this density field to use that to capture the hidden roads. Okay, now how do we extract the mountain ridges? And for this, we're going to use the one stable manifolds of F from the Morse theory. Okay, so I'm not going to give you the full introduction of the Morse theory, just some basic notations here to explain what is the one stable manifolds. And also for this audience, I assume that many of you know this very well. Okay, so let's say we have a nice smooth function F defined on RD, okay, real valued function. The gradient of this function F at a point X is simply, so this is the X here, okay? The gradient at this X is simply indicates the descending direction of function F, okay? The magnitude of this vector indicates the rate of the descending change of F in this direction, okay? The critical points of the function are those points where the gradient vector vanishes. Okay, so in this example where we have a function defined on R2, we have minimum, saddles, and maximum. Minima blue points, saddles are green points, and maxima red points. Okay. Now, the integral line on this domain are those maximal paths, such that locally at any point, the tangent of your path is agrees with the gradient at this point. Okay, an informal way of thinking about this is that the integral line basically is that if you drop a water on your terrain surface, okay, and then see where does the water flow to. Okay, this flow line basically traces out to the integral line. Okay, so that's the intuitive description of the integral line. Now, this integral line, they keep going till then you have no place to flow to. That means that it ends at a critical point. We call this the destination of this integral line, okay? You can also go the opposite direction, keep going up till you have no place to go where the integral line ends. And that also has to be a gradient, a critical point, because that's where the gradient vanishes. Okay? In other words, the integral line will start from a critical point and ends in the critical point. Okay? So in this 2D example, generically, most of the integral line, they would start from a maximum and end at a minimum, like that water or flow into a certain basin, a valley represented by this minimum. Okay. However, sometimes some integral line, they would actually flow into a saddle point. They would start with the maxima and end at a saddle point. Okay. So the one-stable manifold are basically the for the saddle point is basically the integral line that ends at the saddle point. Okay. So in this picture, for this saddle point S, the integral, the one-stable manifolds of this consist of this two pieces of 1D curves. Okay, so in general, if your function is defined on D-dimensional domain, then in the one-stable manifolds at the integral lines ends at index D minus 1 saddles. Okay. Now, why are this kind of intuitively capture the mountain ridge? Now, let's look at this picture. So here, this S is the saddle. I have two maxima, M1 and M2. Okay, so this is basically the, what happens is that consider this point X. Okay, if you move a little bit to the one side of X, that will then the flow would flow into one valley, probably on this side of the mountain. Okay, but if you move a little bit to the other side, then you would flow into a different valley. Only at this moment you're going to trace out this one-stable manifold to the saddle point, and this is like the mountain ridge. Basically, if you look across this green curve here, on either side, you're going to descend, going down. Your function value is going to go down. You're going to go to different valleys. But along this, you would, starting from the maximum mountain peak, you're going to go to some saddle. Okay, so intuitively, this one-stable manifold kind of captured the mountain ridges that we aim to describe. Okay, so here just the one example on a real terrain. The black curves are the one-stable manifolds of saddle point. Okay, all right. So that was the intuition behind that. Basically, what we said is that given the input GPS trajectories, I'm going to convert it into a density field. Okay, and then look at the terrain, the graph of this density field. I want to capture the mountain ridges in this terrain, which is further extracted by using the one-stable manifolds of this function. Okay, so this is fine, but this is introduced in the smooth setting. We assume that we have a nice smooth function on the planet on the input domain. Okay. What happens in the discrete case when our input is just a triangulation, or more generally, just be a cell complex? Okay, now. Let's assume that our input now is a triangulation of the domain, and the function value now is only given at vertices of this triangulation. Okay, we could try to extend our function to piecewise linear function, and then use PR approximation of the one-stable manifold in the smooth case in this PR setting. Okay. So we can do that. This can be done, and especially in 2D, I think this can be done in general, but in 2D, the software has been produced. Okay, but however, this becomes numerically complicated, especially later if you want to simplify your one-stable manifold. This becomes complicated for dimension higher than 2. Okay, so what we are going to now to handle this discrete setting, instead of using a PL approximation of the smooth setting, we're actually going to use the discrete Morse theory introduced by Foreman. So this is kind of combinatorial version of the Morse theory. Foreman proved many beautiful results analogous to the classical Morse theory setting. And this works for general cell complexes, but let's assume in our implementation, we have a simplicial complex setting. Okay, because the whole theory is combinatorial, it's numerically very stable from the implementation point of view. Okay, an algorithm that is easy to handle, especially later when we want to simplify the input, when we want to do simplification of the output one stable manifold. Okay, we'll see that in a minute. Okay, so now I will not describe actually. So there's a discrete Morse function in this discrete setting. Instead, I'm just going to go directly to talk about the discrete analog of the gradient vector field. Okay, so these are kind of equivalent. So remember now our setup is that we're given a simplicial complex K. Okay, now a discrete gradient vector is actually a pairing between two simplices, sigma and tau, where sigma is the phase of tau. Okay, so in fact, the dimension of sigma and tau differ only by 1. Okay, so for example, you could have a vertex paired with an edge that this vertex is incident on. That's a discrete gradient vector. Or you can have an edge and a triangle pair. That's also a discrete gradient vector. Okay, so now as you see, this vector in code really is the combinatorial pairing. Okay, it's a pairing between two simplices. Okay. Now, a Morse pairing is just a collection of such discrete vectors where each simplex can only participate in at most one such pairing. Okay, so each simplex can only be used once. Okay, and now, if a simplex does not participate in any of the pairing, in other words, it does not participate in any of the discrete gradient vector, that's kind of analogous to say that this simplex, my discrete gradient vector vanishes. Okay, in which case we say the simplex is critical. In this example, this pink colored triangles, vertices and edges, this simplices, they do not participate in any discrete gradient vector, and all of them are critical. Okay. Now you can also talk about kind of gradient vector paths formed by these vectors. Okay, so for example, in this picture here, this is basically, it's just a sequence of simplices between index p with index p plus 1, where let's look at this example. Say, starting from this edge is edge paired with this triangle, and the next edge is some face of that triangle, and then you continue. Okay, so such a path is called a V path. This is basically the discrete analog of the flow line, the integral line that we saw before. Okay, basically you keep following the gradient vectors to get a path. Okay, and now in the case of Morse theory, we know that if you follow integral line, in fact, they intersect each other and they cannot form loops. Okay, cannot form a cycle. Okay, so that means that in the discrete case, if I look at such a V path, okay, I don't want this to be cyclic. I don't want it to come back to itself. Okay, a V path which is not cyclic, if it's acyclic, then we call this a gradient path. Okay, finally, I'm ready to introduce the discrete gradient vector field. This is basically a whole bunch of a collection of discrete vectors, okay, such that there's no cyclic V path. In other words, it behaves like a gradient vector field. Okay, so you should feel free, if you have questions, feel free to interrupt me and ask. Okay. All right. Now, as I said, there's also a concept of a discrete Morse function, where it is also combinatorial in the sense that every simplex in your input simplicial complex will receive a function value instead of will receive a function value. Okay, these two are roughly equivalent to each other in the sense that given any discrete Morse function, it will induce a discrete gradient vector field I just described, and given any discrete gradient vector field, you can find a discrete Morse function that induces it, okay? But just to summarize what I just said, we care more about this discrete gradient vector field, okay? As I said, this you can think of this as a discrete version, analog of the gradient vector field for the Morse function, okay? Interestingly, inside if you have a critical K simplex in the discrete gradient vector field, that kind of corresponds to an index K critical point in the smooth case, okay? So if we have a triangulation of R2, which is like in this example that we're showing here, then the critical triangle kind of corresponds to a maximum, critical edge corresponds to a saddle point, corresponds to a saddle in the smooth case, and critical vertex corresponds to a minima in the smooth case, okay? Now, we wanted to extract the one stable manifold. Those are the integral line that flow into the saddle, which means that they need to flow into the critical edge in this case, okay? In this discrete Morse theory, actually, they consist of edge triangle gradient paths, vector paths. Okay, now we can compute that, but algorithmically this is not very easy to maintain. So from now on, just so that we have a simple algorithm, actually I'm going to take the inverse of our function. So mountain peak now become valley. Okay, so now instead of trying to mountain ridge, I want to identify the valley region, namely those going from valleys to saddles, to another valleys, to another saddles, and so on, okay? The reason is because in this discrete setting, there's one unstable, this is so-called one, kind of corresponds to the one unstable manifolds in the Morse theory. It's because in the discrete setting, the one unstable manifolds consist of a vertex edge vector paths, which is much easier to compute and maintain, okay? In fact, later, no matter what your domain, the dimension of your domain is, in order to compute this one unstable manifold, we only need the two skeleton of your input simplicial complex, because we only extract the vertex edge V passes. Okay? So here an example.
That's very nice. Just a quick question. So in this in this discrete setting, you can distinguish, as you just explained, the one stable from the one unstable manifolds. In the continuous version, that's not as immediate. You sort of need to know where you started or where you're ending. Is that right?
Oh, no. So one unstable manifold actually is defined as follows. So remember that every integral line, if you integral line is a maximal path where kind of a maximal extension of the flow path, right? So every integral line has a starting origin, a starting point, and a destination, okay? So the one unstable manifold is just those integral line that starts from index 1 saddles.
Thanks. Yeah.
Does that make sense? Okay. So in this picture, I only have the discrete setting. You see that for this red edge E1, the one stable manifolds to it are these two blue paths. They consist of edge triangle paths. Okay. For this critical edge E2, this red edge here, the one unstable manifolds consist of this vertex edge path, these two blue paths. We didn't finish. Okay? Yeah. All right. So the change here really changed from the density function to the negative of the density function. It's just so that one unstable manifold is easier to compute algorithmically. Okay. Now, one important advantage of using this discrete Morse theory here is actually, let's say that we want to simplify some of the, there are too many critical simplices, we want to simplify our discrete gradient vector field, okay? And there's a nice combinatorial operation to do that, which is what I call the Morse cancellation operation, okay? In particular, if you're given a pair of critical simplices, in this case, consider V2 and the E1. V2 and the E2. Okay, so these are red, both of them are critical. Okay, if there's a unique gradient path between them, like in this case, I have only a unique gradient path going from E2 to V2. Okay, you can think of this is flowing down in terms of the function value. Okay, to cancel this pair of critical simplices in my discrete gradient vector field, all I need to do is that I basically take this path, I kind of invert it. So when I invert it, I actually pair V2 with this first edge, and then pair this vertex with the second edge, and then pair the third vertex with the edge E2. Now you see that after I do this inversion, both V2 and the E2 are no longer critical because now they also participate in discrete gradient vectors. Okay, so from this point of view, I simplified this pair of critical points. Okay, and you can do so for any pair of critical simplices as long as there's a unique gradient path between them. Okay, and the operation is rather simple. It's again purely combinatorial. You just identify this path and then you reverse the pairing. Okay, change the pairing a bit. Now the only condition is that there has to be only a unique gradient path between them, because if there are two, like which is what I indicate here. Okay, in this case you cannot simplify the pair of critical simplices S and T, because if you invert one of them, afterwards you're going to have a cycle in your gradient path. Okay, so which is not valid anymore. So as long as there's only unique gradient path, you can simplify them. Okay. All right. So what I said is that we have this purely combinatorial version of Morse theory, where the gradient vector and everything is all combinatorial in some sense. Okay, and you also have this powerful operation, this Morse cancellation of critical pairs, which can help us to simplify the discrete gradient vector field, which will further in turn simplifies the one stable or one unstable manifolds that we aim to extract. Okay, now the question is that, but which pair of critical points should I cancel them? Okay, you can actually cancel any pair as long as there's a unique gradient path between them. Okay, but we want to cancel them intuitively. We want to cancel those less important ones according to our input function, right? So we want to only cancel the less persistent one. And now you see where the persistent homology is coming into. How do we decide which critical pairs are important and which are not important? We're going to use the persistent homology induced by this input density function to guide the cancellation of critical pairs. Okay. Now, for this audience, I assume that I don't have to talk about persistence at all, but let me just point out that here, we have an input function. Remember, that was the density function, even though in this example, I'm just drawing a function defined on the line, on the real line. The persistence I'm talking about is the so-called sublevel set persistence, the one induced by looking at sublevel set filtration. Okay, in particular, imagine that you sweep the domain in increasing function, increasing function values. At any moment, you track what is the topology in the sublevel set, which is the portion of your domain whose function value is below the current function value A. Okay, and as you sweep this domain, and the topology is actually captured by you look at the homology of the homology group of the sublevel set. Now, as we in this simple 1D example, as we pass through minimum, we create new zeroth dimensional homology connect components, and as we pass through maxima, we merge some connect components, and the persistent homology help us to pair them up. Ultimately, the output of after we finish the entire sweeping, the output of persistent homology, persistent algorithm will give us a set of pairings between critical points, okay, where each pair, in this 1D case, each pair is a pairing between minima and the maxima, where the minima creates some components, and the maxima is when this components got destroyed, in the sense it's got merged into a bigger, older component. Okay, so we use this persistent pairing to help us to capture the important or less important features. Okay, now this description again is only in the smooth case. In the discrete case when we have triangulation of a domain. Okay, again, we can think of the piecewise linear extension of the function on the underlying space of the simplicial complex domain K. Okay, now we can simulate what I just said, the sublevel set filtration, using the so-called lower star filtration in this discrete setting. Okay, the original persistent algorithm by Edelbrand, Lecce, and Zomorodin actually does exactly that. And the output of the persistent algorithm will then give us a bunch of pairings between simplices, where the dimension of the simplices in one pair differ by 1. Okay, where say a pairing sigma and tau indicated that the sigma creates some case dimensional homological feature, which was later filled when you introduce the simplex tau. Okay, the persistence of this pairing is just the function value distance between them. Okay, now the interesting thing is that if your PL function is kind of a PL approximation of a smooth Morse function, as we see in the previous example, okay, roughly speaking, if you look at all the persistent all the pairs of simplices output by the persistent algorithm, okay, those with strictly positive persistence actually corresponds to the pairing of the critical point that I just described in the smooth setting. Okay, another way to say this is that the persistent algorithm will actually pair up all simplices. Okay, every simplex would participate a persistent pairing. Potentially can be paired with infinity, which means that this one would create essential homology. Okay, but many of them actually has persistence 0. This kind of pairing corresponds to that you have a simplex paired with within the lower star of. Okay, so think that you have a triangulation of the surface. Okay, imagine that I add a vertex and all the triangles incident to this vertex, where all the function value are lower than this vertex. Okay, this is called the lower star of this vertex. Okay, those 0 persistence basically indicate the pairing within this lower star. Okay, so they're just the local structures. If you look at the persistent pairing whose persistence is strictly positive, then those are the pairings corresponding to this pairing between critical points that we see here. Okay, we're going to use this later. All right, so now I'll introduce all the ingredients to show you the algorithm. The algorithm is rather simple. So assume that our input now is the triangulation K of some domain Rd, together with a density function F, which is only given at vertices of this triangulation, okay, and also a implication threshold delta. Okay, now what we do is as follows. Okay, at the beginning, I don't yet know at the beginning, I'm going to do something simple. I'm going to initialize the discrete gradient vector field on this triangulation K to be the trivial one, in the sense that every simplex at the beginning is critical. Namely, I don't have any gradient vector at all. Okay, then I compute the persistence pairing induced by the sublevel set of the minus F function. Remember that we want to take the negation of the density function, so we capture the valley regions. Okay, then I'm going to use, so the output of this step is a bunch of pairing between simplices. Okay, each one has a persistent value. Then I'm going to, for every pairing of simplices whose persistence is smaller than delta, okay, I'm going to process them in order. And if I can find a unique gradient path between them, then I simply perform Morse cancellation to cancel them out. Okay, in other words, my goal is that I'm going to now cancel out all the critical pairs from the output of the persistent algorithm whose persistent at most delta. Okay, so I want to simplify all those critical points. That's what we want to do. Okay, but I have to check whether indeed I can cancel them in the Morse setting or not, whether there's a unique gradient path between them or not. Okay, as I do this cancellation, I keep update my discrete gradient vector field. Okay, so that's the second step. I simply cancel out, perform Morse cancellation for all the persistent pairings whose persistence is smaller than delta. That's it. Okay, in the third step, then for all the remaining critical edge whose persistence is bigger than delta, okay, in fact, we only look at the positive critical edges. Yeah, for all the remaining critical edge whose persistence is bigger than delta, now I simply collect their one unstable manifolds from the current discrete gradient vector field, okay, as the output. That's it.
Yusu,
Okay.
Yusu, could I ask
yes.
a question? Yeah, so from step, right before step 1, if you start with a discrete gradient vector field that is trivial, then everything is critical. So I'm curious, or maybe I'm misunderstanding something. How is it possible to do simplification when everything is critical at the beginning? Where does the first gradient vector field come from?
Yeah, so this is a very good question. So what happens is that, let me answer your question actually in 2 ways, okay? Number 1, actually, this is the one motivation of studying this problem, because we put persistence together with the Morse, discrete Morse theory, but a prior is not clear that these 2 procedures necessarily match with each other, okay? So we wanted to understand exactly what happens, okay? Now, to answer your question, what happens is that at the beginning, there's everybody is critical, okay? Now, on the other hand, what is the output of the persistent algorithm? If you run the lower star filtration, okay, the persistent algorithm induced by the lower star filtration, actually, every simplex will participate in the persistent pairing, right? So the persistent algorithm, in fact, will pair up all simplices, okay? And those pairs with 0 persistence, actually, they are the meaningless pairing because that I have this triangulation, if that makes sense.
Yes.
Yes. Right. So after you cancel them out, then, so suppose you cancel all the 0 persistence critical pairs, okay? After that, intuitive, what's left? Now you have the meaningful critical simplices left, okay? Intuitively, now the critical simplices corresponds to the real critical points of the PL function.
Okay.
Does it make sense?
So I guess to understand what you're saying is essentially where on step 1, when you compute the persistent pairings, the 0 persistence pairs would give you some initial directions of the gradient field based on functional differences.
Right.
And then that's actually, so okay.
I should have included a picture here. Actually, this is a very good point because in some of the earlier work, for example, in Vanessa's work, instead of setting it to be trivial, they directly set up initial discrete gradient vectors based on the function value, which essentially is guided by this lower star filtration. Okay, but then since it's all local, so they know how you should pair them up. So instead of go through the persistence step, they say, I directly set it up. Okay, but we present it this way also because it's just conceptually it's very clean. Okay, so you start with the trivial one, and then you just keep doing simplification, doing Morse cancellation. That's all that's involved. Does it make sense?
Yeah, thank you.
Yeah. Okay. Sure. All right. So this is the algorithm. It's rather easy to implement, especially in 2-dimensional case. And I should say that this algorithm works for domain I in any d-dimensional space. But the algorithm only requires the 2 skeleton of the input triangulation. Okay. All right. So here's some examples. So these are the GPS traces from Athens, from Beijing, from Berlin, and that's this blue trajectories. And what you see here are the dark curves are the reconstructed road network by our algorithm. And what you see underlying the thin network, those are the true map. Okay, of course, we don't cover everything in this true map because our samples do not cover everywhere in the true map. Okay, this is just to show you the effect of the persistence. So this is from the Berlin data sets. Now this is A is the original the reconstruction using a very small persistence threshold. So you can see a lot of details. And as you increase the persistence threshold, we see only the main street and the backbone of this road network. Okay, and now I want to remark that just simply doing thresholding, even if you try to do some intelligent thresholding, is not so trivial because, like for this data set, for example, the downtown area has much higher sampling density than regions like on the side. Okay, so if you want to use thresholds in order to capture details in the downtown area, you have to then use a very high threshold in order to be able to. Otherwise, the downtown roads in the downtown area completely collapse. Okay, but then when you use a very high thresholds, you don't capture the details in this right side of the map. Okay, so it's challenging to even adaptively to choose some good threshold for the reconstruction purpose. Okay, this is to point out that I think really the main advantage of using this approach is that when we do the reconstruction, we kind of have the entire input, because we're looking at the topology of the entire density map. Okay, so you have the global structure, you're inspecting the global structure captured by the density map. And because of that, the output tend to be more complete. Even if you have small gaps, the algorithm can still reconnect through it. Okay, while the previous approaches, since most of them are based on local information, so this is actually one of the state-of-the-art of algorithm previously, the output tend to be broken into small pieces because they use the local information. Okay, this is just I'll just point out, I'm not giving the algorithm here, but the same framework can be used that if you have two different reconstruction, like in this case is our reconstruction, this is a reconstruction by one of the earlier methods, but maybe they capture different portions. You can also use a discrete Morse based framework to do the map integration, to integrate them into a more complete map, okay? And you can also do the augmentation, which essentially that, in this example, this is in Beijing map, around this highway complicated intersection, we don't reconstruct it very well. But then if you have someone manually just label those parts, you can augment the reconstruction network, which is this black curve or the blue curve here, with this input manually constructed input by the user. You can merge them together, okay, augment your map, okay? As I said, the algorithm works also for a higher dimensional case. Here we're using this to reconstruct the neurons from 3D images, okay? I'll skip this here. Now, what I said so far is that this framework, in fact, especially on the road network case and on the neuron case, it's a very simple framework, but it really works. And it also simplified both conceptually and implementation speaking, simplified how we approach this problem. The algorithm is rather clean, okay? But then you can ask that, okay, it works in practice, but what can we guarantee? What can we say? Okay, why does it work? Okay, so we aim to answer some of this question now. In particular, I see that I'm running out of time. Okay, so so we try to answer this question, okay? And in particular, based on the theoretical understanding, we can actually provide even further simplification of the framework that I just showed you, which I'm going to explain. And we also can provide theoretical guarantee of the reconstructed graph compared to, say, a true and hidden input graph under simple noise model, okay? Now, let me just point out that based on the understanding of what can be reconstructed, we can actually develop a very simple editing strategy to allow us to add missing parts in your reconstruction. Okay. In particular, if I miss, so here the blue is our reconstruction, and the red is what we added interactively. So if you miss some branches, you can just click a point and make it a local maximum, and that will enforce that we would connect this through a branch to your road network. Okay. Or if you miss some, like in this region, we miss a lot of local roads forming loops, you simply click a point in the middle, set a triangle to be a local minimum, and then that would help you to reconstruct a loop structure around it. Okay, so, but let me talk about the simplification of this algorithm. Okay, now just to remind you, we have 3 steps. The first step is to compute the persistence. Then we use the persistence to help us to decide which pair of critical points to be simplified. Okay. However, currently in this step, presumably, if I want to simplify a pair of simplicities given output by the persistent algorithm, I still need to check whether they are indeed cancelable or not. Namely, is there only a unique gradient path between them? Okay. It turned out that actually we don't have to do that. Okay. Number one, we don't. So the critical pairs can be between vertex edge or edge triangles. We're only taking the 2 skeletons of the input domain. Okay. It turned out that actually for our output, since we only want to reconstruct the one unstable manifold in the future, okay, for our purpose, we don't even need to cancel edge triangle critical pair at all. Okay. We don't need to cancel them explicitly, that is to say. Okay. We only need to cancel the vertex edge critical pairs. Okay. Furthermore, even if I need to cancel vertex edge critical pair, I don't need to check whether it's really valid or not. It turns out that they're always valid. Okay. Now, what's more, I don't even need to explicitly check and do the cancellation. Okay. It turned out that in order for us to maintain all the information about the discrete gradient vector field, that's sufficient for us later to reconstruct the one unstable manifold. Okay, all I need to do is that I look at from the output of persistent algorithm. Okay, I take all the negative edges, namely those edges paired with vertex. Okay, and I take the collection of them whose persistence is smaller than delta. Okay, the collection of such negative edges whose persistence is smaller than delta form a spanning forest of your input simplicial complex. Okay, I simply collect this spanning forest, and this is sufficient for me to go to step 3 to recover the one unstable manifold. Okay, in other words, even though that our algorithm is conceptually, we are basically doing the Morse cancellation using persistence to guide us, but to implement that, I actually also only need to scan the edges in the linear time and keep only those whose persistence at most delta. Those negative edges whose persistence at most delta. That's it. I output the spanning forest in this step, and the spanning forest is sufficient for me to recover the one unstable manifold in the next stage. Okay, so that's the first implication. The second is that once we have this one unstable, the spanning forest, the one unstable manifold is very easy for every edge. Though each edge has 2 vertices, I simply find the unique path connecting this vertex to the root in the whatever tree containing this one, and take the union of them. This is the output one unstable manifold for this edge. Okay, again, this step only takes linear time as well. Okay, I should point out that this observation, actually, many of this existed before when in early work when people studied the simplification of optimal simplification of this discrete Morse function, okay, although it's not for this purpose. Okay, all right, so let me just using 2 minutes just to tell you that what is theoretical guarantee that we can get. Okay, so here what we want to say is that if my input data, the input density field satisfies some condition with respect to a true graph, then I want to argue that I can kind of my output graph is close to the true hidden graph that I don't see. Okay, so this is type of result I want to claim. Okay, this requires that I have to specify what is the quality of the input density field. This is what I call the noise model. Okay, we're considering here a very simple noise model, which is that suppose you have a true graph G that you want to reconstruct, which is this red curve in this picture. Okay, assume that my density field is such that there exists a neighborhood of G, which is this yellow region in this picture. Okay, so that my density field is higher in this region than, much higher within this region than outside of this region. Okay, in other words, I mean, somehow this is a kind of, your input is pretty nice in this case. Within a local neighborhood of your true graph, your density is much higher than outside of the place. Okay, and also the variation there is not too large. You can have variation, but the variation is not too large. Okay, this is a picture of this. This is your density field. Okay, so this is going to be our noise model. Okay, so let me skip this. Let me just point out that under this noise model, we can prove that your output graph will also lie within this local neighborhood. So geometrically, it's kind of close to the hidden graph. That's number one. Okay. Topological speaking, that you can guarantee that the output graph has the same first Betti number as the true graph. Okay. And for the case when your input is in a two-dimensional plane, you can have a stronger result. You can actually prove that this local neighborhood deformation retract to the output graph. Okay, so I'll skip all the details here. Okay, let me just point out that this noise model sounds very simple, and it is very simple. This is basically one step better than having a Hausdorff type of error. So in other words, I allow you to have outlier outside of this local neighborhood, but they cannot cause significant density, basically. Okay, so for this specific noise model, you may argue that we could have probably done a threshold approach and still get a theoretical guarantee. Okay, so that's probably true. With some work, a threshold, we can probably obtain a theoretical guarantee using a thresholding-based approach for this noise model. Okay, but I want to point out that the number one, in fact, even if you have clean data, it's not so trivial to prove the theoretical guarantee using Discrete Morse reconstruction framework. Okay, number two is that the performance of the algorithm is actually much better than the simple noise model. It's just that our failure of having a better noise model and still prove something of it. As we have seen earlier, that thresholding doesn't really work for the real data. Here's a 3D example where the thresholding doesn't work. Okay, all right. I think I'm really out of the run out of time. So let me just conclude that. In this work, we kind of explored the power of this Discrete Morse plus persistent-based framework for graph reconstruction. Okay, we have implemented the algorithm run for 2- and 3-dimensional cases, but in principle, the algorithm works for any dimensional domain. And we also provided some theoretical guarantee of the reconstruction ability. The current this is only a first step. The current noise model is very limited. It'll be interesting to see how to build a more general noise model where we can still prove something. Okay, and another one, subtle point that I want to mention is that this approach is actually not always effective at reconstructing panning branches, especially if your density continues to decrease along a branch. In other words, there's no critical point on this tree branch. Okay, then this method has some limitation in reconstructing that. I can tell you more offline later if you're interested in what this means. Okay, one last interesting question is that this approach works for high-dimensional case, but in the high-dimensional case, often we cannot afford to have a triangulation of d-dimensional space. Okay, so we have a high-dimensional point clouds as input. How do we, combine all the knowledge in Rips complex and all this to have an efficient algorithm? Okay, all right. Thank you for the attention.
Thank you very much, Yusu, for the fantastic talk. So questions, I have a starting question. This was chatted in from our friends at Michigan State University. So they were asking if they could see some of the videos again. So I think you were showing videos around the slide where you had the neuron picture in 3D.
The neuron? Sure.
Yeah.
So here, let me just, so this data is that, so this is a 3D image stack of some so-called AAV viral tracer injection data. So this data actually, it's not a single neuron. Okay, so there are many injection sites. It's extremely noisy, and this is many neuron bundles going in different way, and the signal strength is very differs. So in this case, we don't aim to reconstruct single neurons. Rather, we would like to have a summary of where does this neurons go in which region of the brain. So what you see, this is the input data, and this is after some pre-processing that the strong signal I'm showing here. So you can see roughly where the signal corresponds to. This is reconstruction after a lot of simplification, obviously. Okay, then we overlay this reconstruction on this is the brain atlas, so that you can see different region of the brain and where does the neuron goes to in these different regions. Basically overlap this into the brain atlas. Yeah, the connection atlas, yeah.
Oh, that's a very cool application. Other questions for Yusu? So I have go ahead.
Yeah, so, sorry, I was going to ask one more question surrounding the simplification of the algorithm. You mentioned that you actually never perform any simplification. You just extracted the minimum spanning forest. And is my understanding correctly that in the situation where in the minimum spanning forest, it's just encode all information of the one-dimensional unstable manifold. So you only need to extract it from those minimum spanning forest. Did I have the right understanding?
Right. So you're roughly right. So what happens is that this spanning forest, okay, this forest consists of those edges, which is actually indeed the minimal spanning forest. So they consist of all the union of all the vertex edge discrete vectors at this point. Okay. In other words, your one unstable manifold can only consist of an extra critical edge together with some paths in this forest. And that is the reason why this is sufficient. So you're right on that. Does it help?
Okay. Yeah, thank you.
Yeah.
Yusu, another question. So your algorithm works with the density data. Maybe in some cases you have the trajectory information of the cars. Are there different algorithms that use that trajectory information? Is that something that people use, or is that not hard? Is that hard to obtain?
Right. So in our approach reconstruction, we didn't actually use the connectivity in the trajectory at all. Okay. But I think that, using that can for sure help to improve the quality. In particular, I show you the Beijing case. We actually didn't do very well at the complicated junction.
Right.
Because also if your street is one way or whatever, so this is okay. So this approach I just described is good at extracting, in some sense, the high level, the roads. If you have very close by roads in different direction, one-way streets, then those directions definitely would help, and especially around the junction nodes, those trajectory information would help. Yeah, there are many previous work which also incorporates those information, which would be nice to incorporate. Yeah.
Other questions for Yusu? Thank you very much, Yusu, for the fantastic talk.